Apologies in advance. This is going to be the worst. All right, here we go. Oh, I need that. All right. There we go. Hello and welcome to the Weekly Space Hangout for Wednesday, October 3rd, 2018. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about a new object in the Kuiper Belt, an exomoon. Masters of the Light, not sure what that's about. And of course, we're going to all oogle over some pictures of Hayabusa and all the cool stuff that's happening down on the surface of Ryugu. Joining me this week, we've got, I don't even know how to make this work, Dr. Paul Sutter.
Hey, it's me. I'm Paul Sutter, author of Your Place in the Universe, which I promise is a very good book. Astrophysicist at Ohio State.
And we've got Dr. Morgan Renberg. Morgan.
Fraser, it's good to see you in your slightly blurry natural state. You were too sharp and real last time.
He's like that in real life. He's like that in real life, I think.
Yeah. We were hanging out at the Astronomy Cast 500 episode, which is a whole other thing, as well as getting a chance to meet Dr. Kimberly Cartier for the first time, IRL. Kimberly.
Hey, Fraser, it's good to see you back where you belong, behind the screen.
The screen as opposed to...
No, it was great hanging out with you and Morgan and Pamela all at AC 500. Now I'm
Happy
just back.
podcast day.
Happy podcast day. Oh my gosh, it's been so long since I've had a podcast day. I've missed it.
Yep. Well, I guess we did a temporary episode, but now we're back with the real episodes.
It's the real podcast.
This was the
day
impromptu
now.
one in a bar. And joining us as a special guest this week, we've got Dr. David Warmflash. David, welcome to the Weekly Space Hangout.
Hi, everybody.
David and I have actually, I think you are one of the longest time guest coordinations that I think we've worked on. You and I had been trying to go back and forth a bit, trying to figure out a time that you were going to be able to make it on the show. And I think we had been talking, I'm going to say we've been talking
I
for...
think I wrote the last 60% of my book during the intervening time.
Yeah, exactly, yeah. So for people who don't know who you are you and what do you do?
Well, I am star stuff that has achieved consciousness. But I'm an astrobiologist and space medicine researcher, and especially for the last several years, a science communicator as well. And I still do some research and I go back and forth. And I'm on some proposals, so we'll also see. And I don't have a book to show up because it's another 7 months before it comes out.
Yeah.
And I'll have something like he had, so I can hold it up on camera.
Well, make sure that your publisher gets a copy out to us, and we'll give you a shout out when it arrives.
Well, I can send you the edited manuscript and the how the cover's going to look.
Yep.
But they'll have that free book that all the journalists get. I don't know what point they'll have that.
That sounds awesome. Now, apologies. You're shooting. I think you're shooting this from your phone, so. I know the audio quality isn't as good as it could be, so just
Let's move up more. Yeah, I'll shout.
Yeah, there you go. Shout. That's all you got to do. And that's why we have microphones like right in front of our faces. So now let's talk about a couple of the topics. So first, let's talk about the astrobiology of things. Now, actually, what is the book that you're working on?
This book is called Moon, An Illustrated History, and it's by Sterling Press. That's a subsidiary of Barnes & Noble. And it's because, we got a big 50th anniversary coming up next year, 2019, of 1969, the year the Mets won the World Series. But it's also an anniversary of a few space exploration milestones. We had Apollo 9, Apollo 10, Apollo 11, and Apollo 12, all in that same year, and a few interesting Soviet missions as well. Really, what's driving all this in the public light is, of course, Apollo 11, because that's the mission that people outside of this sphere have heard of. Your person on the street probably doesn't know what Apollo 10 did. or what Apollo 12 did.
Did you think that we would cross this line where we get to 50 years since Apollo 11?
Well, I thought we would get to it,
And with no missions,
not,
with no
yeah,
missions
and
since the Apollo missions, like do you
no
think that
people back to the moon.
line would cross and there wouldn't be any more follow-up missions to the moon?
I didn't think that when I was a kid. A year ago, I thought that. Well, yeah, it's a little bit depressing, but I think we are going back finally. That's where things seem to be going.
And I mean, did all of the Mars? Well, hold on a second here, I lost that. Oh, did all of the new Moon Mars plans that NASA is proposing, the president is proclaiming, did that sort of, where does that enter into your thought process right now? Do you think we're ready to go back to the moon and Mars, and then on to Mars?
Well, we're ready. As people, we're ready. We're not ready with the hardware yet, but things do seem to be going in that direction. The Orion SLS system, NASA is very slow and careful, but that's a good thing. And if the funding doesn't get caught, then it looks like people will be going into orbit around the moon through cislunar space, and maybe to asteroids, and there'll be the Gateway Station, or it's called something else now. There's no lander capable of humans because the Altair lander, as you know, I'm sure, was canceled. So there's a lot of magazine articles and so forth about how now humans will go back to the lunar surface, but do you see a lander to do that? Not yet, but
well, actually, today, I don't know if you've been seeing the news, Lockheed Martin just released their latest photographs of a new lander that they want to send to the moon. It's a monster. Like 22 tons of lander that they want to put to the surface of the moon. And they just released a bunch of mock-ups and pictures and stuff. So maybe there are plans right now. And of course, the SpaceX BFR should, as just one of the side projects, be able to go to the moon, land on the moon, return from the moon, and be reused again. So who knows if these things are going to actually happen? Of course,
in Musk years.
Right, exactly, in Elonian time.
So that means he's got to have all the hardware ready and get it ready and have all the engine stuff that he knows about ready. And then when it really gets to the point where it could be an actual mission, then start to think back on, oh yeah, there's that radiation thing, and it's kind of really a thin hole compared to what the Apollo crafts were and what Orion is. And now we get to do this radiation modeling and see what the exposure is going to be and all that. But we don't hear them talking about that in SpaceX, not yet. It's not imminent yet.
Now, with your background in astrobiology and space medicine, right at this point, we have orbited the Earth for up to a year with Scott Kelly. Now plans are in the works to go and potentially send humans to the Lunar Gateway. What are the big unknowns that we need to solve to be able to survive in that harsher environment and to return to the moon?
Well, there are the big unknowns related to long duration, which in terms of going to the Gateway, we pretty much have answered those on ISS and on Mir, because we're at the time that people will be in cislunar space is not going to be any longer than they've been in low Earth orbit, except that you have the radiation. Really, that's the only difference, because it's a different radiation environment, as you know, if you're beyond the geomagnetosphere. In terms of the listeners, is that something I should explain?
No, they understand.
They pretty much, yeah. It's just in terms of the health risk, there are a lot of unknowns, because the longest mission was Apollo 17, the longest mission with people. Everything else is just, we have a little hint of this and that. Hubble is at a very, very high, that repair mission that was at a high altitude, but that's not enough. We really don't know. And everything is extrapolated when it comes to radiation health. the idea of what are the effects of low dose radiation or low medium dose radiation is so much based on extrapolating backwards on a curve based on higher exposures and how those associate from, let's say, the atomic bombings of Hiroshima and Nagasaki and the Chernobyl accident and Fukushima. Really, those data aren't really that useful because there really, luckily, wasn't really too much of a health effect from the radiation. It was a lot from the tsunami and from people rushing around and the evacuation and even heart attacks from people stressed out. So really we have Chernobyl and those the bombings. And based on that, they've drawn curves and extrapolated backwards, add into that some data from medical imaging like full body CT, computed tomography, and try to put stuff together and then extrapolate with an assumption that's called a linear no threshold model, which means it's the idea that if a high amount of radiation, a high dose, it gives you a high risk of cancer and other health effects down the road and stochastic effects. And a medium dose gives you a medium risk of those health conditions. Well, then a low dose must then give you a little bit of an increase, and that's a big assumption. Mm-hmm. And there's actually debate about this in the radiation safety community that maybe the linear threshold model is wrong.
I'd heard that.
There might be a threshold.
Yeah, I'd actually heard that. And I know like this idea that maybe a little bit of radiation is good for you but a lot of radiation is bad for you. I mean, these are just questions that need to be investigated and sorted out, and people need to, we just don't have enough data right now. And the problem is that you have to, if you're going to try and gather that data, you're going to have to radiate people, which...
Yeah, and if you search for long-term effects and low-dose radiation, there are some papers, but there is a really low number of peer-reviewed papers, and there are data suggesting that low doses actually have a protective effect. It's called radiation hormesis, but it's just a huge area, an unknown area, and we don't know. We have to fill in the holes. And it could be that certainly the amount of radiation that we receive on Earth, on the surface, is not harmful at all. And you could probably go a little bit up beyond that, and it might be good for you at some point. And then you keep going up, it'll be bad for you. And of course, it depends on what kind of radiation. If you're talking about Hg particles, it's very different than if you're talking about gamma radiation, or if you're talking about other types of particulate radiation. You're talking about an iron nucleus going right through your brain. You are talking about getting rid of brain cells.
Yeah.
So there's problems about that. There's astronauts see flashes. Even when they're in LEO, they see flashes, and that's because of particles hitting the retina. So, what does that do to the eye? This is a very big unknown. And there'll be an unknown in the gateway. But what's pretty much assumed is that once we're on the lunar surface, that will be underground for protection. Same thing on Mars. So when you see these artist depictions of the Martian colony, and you see these beautiful domes, well, the people won't be in the domes except once in a while for a quick visit. The farms will be in the domes because they need the light, but everyone else will be downstairs in the kind of shopping mall underground conditions. So when people get so excited about colonization of Mars, and I'm not against colonization of Mars, but they have to keep in mind that when you say, well, that's better than the moon, well, it's going to look exactly the same living in a moon colony as living in a Mars colony. You will be underground.
Yeah, as living in the desert, under the desert, on Earth, like you're just going to be in rock.
Yeah.
Deep rock
and
mining.
We don't know. There's a huge unknown in terms of the fractional gravity. We don't know if there's an advantage of Martian gravity over lunar gravity. We don't know, especially in terms of reproduction. We know from animal studies and from human studies to a certain extent that the gravity axis is important for the orientation of the conceptus and through embryology especially. And we don't know what's going to happen if you go down to Martian gravity or lunar gravity. If we were on the moon doing research, we could have centrifuges and simulate Martian gravity, but we can't do that on Earth in any good way. We're pretty sure Venusian gravity would be just fine because it's so close to Earth if we had these floating cloud cities on Venus. That wouldn't be a problem in terms of gravity.
Yeah.
But we really don't know about Martian gravity.
And I think that's the real big part of this, is that we just don't know anything. We just don't know anything really, and we definitely don't know what we think we know to a level that that we're willing to risk human lives on. So so it's time to go back and run some more experiments and see what we can learn.
Although there might be some rationale to risking human lives if these are volunteers, just as we do with astronauts. But if you're talking about switching from a base to a colony, and you're talking about having children, that is a whole different thing.
Yeah.
Then the ethicists have to get involved. You got to be really, really sure you're not going to be creating suffering because of this. And we just don't know. I think we will learn, but it might take another generation or two before we're ready to
David, I mean, let's talk briefly about your book. When will we get a chance to see it?
It's right now the date for the release is May 7th, and hopefully that won't shift. That's what the publisher keeps saying, and it'll be in bookstores.
And that puts you a couple of months before the 50th anniversary of Apollo 11.
Yeah, it puts me nicely with the 50th anniversary of Apollo 10,
right? When
they almost landed, but they couldn't land. It was too heavy. The LEM was not heavy enough to make a landing and get back. They could have landed, but they wouldn't have been able to get back. So that probably explains why they didn't yield to the temptation.
Yeah. Well, so David, what's the best place for people to find out more about you?
Well, you could go to my Twitter feed, Cosmic Evolution, and the Moon book has a Facebook page in its infancy. It's an embryo right now. I think it has about 30 or 40 likes or something because the publicity really didn't get started yet. I write for several different, I'm a contributor to different things. Scientific American, to this recently Leaks magazine. I have 2 articles on there so far. I have a whole string of things on something called Genetic Literacy Project, which attempts to teach about this whole issue about agricultural genetics and science versus fear and all that. But I don't write so much on the agriculture. I write more on gene therapy and that sort of thing.
Yep.
What else? A few different things I can't remember.
Well, I've directed people to your
Medscape, but which is really just for doctors to read.
Yeah.
That's part of WebMD,
yeah.
And a few things like that.
Oh, great. Well, I've shown people copies of your Twitter feed here, so I'm sure if people want to find out more, they can follow you there.
Yeah, please follow me. I need way more followers, says my publisher. I need to bring it up 1 order of magnitude, and then they'll be really happy.
Well, you're getting the Weekly Space Hangout bump right now, so so there you go. You're halfway there. All right. Well,
Is
David,
that an order of magnitude?
yeah, thank you so much for joining us today. Really appreciate it. congratulations on everything you've done so far. Thank you for talking a bit about this, and each one of those subjects we could have spent a whole an hour on, and I'd love to ping you again when the 50th anniversary happens, and even
Sure.
when we're starting to look
Sure.
at the medical repercussions of sending humans back to the moon. So we'll talk to you. We'll
The
definitely be talking to
anniversaries
you
are
later.
coming up. I mean, you got Apollo 7, but you got the 8 coming up in December.
Yeah.
It's a really big mission.
That's a good
was
mission.
Yeah.
All right.
Yeah.
Thank you so much. We'll talk to you later. All right. Now it's time to get on with the news this week. Let's see. Oh, I really want to talk about Hayabusa. But first, before we do that, Morgan, let's talk about the super elliptical Kuiper Belt object.
It's in the Kuiper Belt. It's super elliptical.
Goblin.
And it's
Wow.
it's a goblin apparently.
Can someone define super elliptical? Like, is it? I didn't know there are different kinds of elliptical.
Yeah. So just to be a little more clear, we're talking about an object called 2015 TG387, which has very cleverly been nicknamed the Goblin, I guess because T and G are at the front of the name. And I think its eccentricity is maybe like 0.94.
Wow.
It gets as close as 65 AU from the sun, but as far as 2,300 AU. And we're looking at it right now about 80 AU away. So it's very, very close to the sun right now in comparison to where it spends most of its 40,000 year orbit. And so we're lucky to have caught it right now because in a few thousand years, it'll be so far away that there would have been no hope to see it, even though it's about 300 kilometers in diameter.
So if it's so far away, does that actually still qualify as a Kuiper Belt object, or is that Oort cloud?
So I think there's a lot of sort of definitional problems right now in this part of the solar system, right? So we have the inner solar system, we have the outer solar system, we have the Oort cloud, we have the Kuiper Belt, which starts roughly at the orbit of Neptune, around 40 AU, and goes out maybe to like 50 or 60 AU, kind of depending on how you write your definition. Then we have what's called the scattered disk, which stretches from the edge of the Oort cloud, I have Oort cloud on the mind here, the edge of the Kuiper Belt out to some nebulous distance, and we call it the scattered disk because now things are starting to kind of break down and out of the orbital plane. The Goblin, for example, has an inclination of about 12 degrees, but we see a lot of objects out in the scattered disk that are much more inclined than that. And then somewhere out there, maybe around 1,000 AU, you transition into what we'd call the inner Oort cloud. And then the inner Oort cloud might extend from like 1,000 AU out to many thousand, 4, 8, 10,000 AU, to what we'd consider sort of like the big Oort cloud, which could start 10,000 AU out and extend halfway to the next star. But other than the definition of the inner and outer edges of the Kuiper Belt, there's not really an agreed upon answer to what we would call this part in space, other than really, really far away.
But, I mean, when you think about Sedna, I remember when Sedna was first discovered, it was this dramatic... We were super lucky to catch it. It had an enormous orbit. We were really lucky to catch it.
600 AU, I think.
Yeah, that the point that it was at the closest point on its orbit, and the Goblin is just ridiculous in comparison.
Yeah,
It's
I
so
think
much
there's
farther.
there's maybe one known Kuiper Belt object that's farther away. It doesn't have a cute name like Sedna or the Goblin, but it could have its aphelion, or the point farthest in its orbit farthest from the sun, at over 3,000 AU away, but that's like plus or minus 1,000. So we don't really know for sure, but this is certainly at least the second farthest object that we've observed in the solar system. And what has gotten everyone's attention here is that not only is it the second farthest away, but its orbit is sort of aligned similarly with this object that's the farthest away, and aligned similarly with Sedna. We've found them all at about the same part of space, sort of 60 to 80 AU away from the sun, all with their orbits kind of tipped in the same way, aligned in the same way. And this is kind of the fundamental argument that people use to say that there must be another planet out there way beyond the orbit of Neptune that we call Planet 9. The idea here is that the relationship between Planet 9, orbiting about 1,000 AU away, and these objects is basically the same as the orbit of Neptune and the orbit of Pluto. Or you can imagine the orbit of Neptune and the orbit of Uranus. We knew Neptune had to exist in like the 1800s because the orbit of Uranus didn't seem quite right. In the same way, we're starting to find all of these Kuiper Belt objects whose orbits are kind of too similar to be random chance, suggesting that there's something that's helping align them. And Planet 9 is one possible answer to what that something might be.
And so, I mean, I'm sure Mike Brown and team and Konstantin Badigan are excited to have one more data point to run to crunch some numbers, try and find Planet 9.
Yes, so they were quite jubilant in the press release, even though this was not their paper. But the struggle kind of still remains to find Planet 9. Given how big space is and how small Planet 9 would appear on the sky, and presumably how faint it would appear on the sky, we have to know really pretty closely where it might be, which, again, we did know, for example, when we were using Uranus to find Neptune. They could calculate down to a real small part of the sky to say Neptune be there, and there it was. This problem is, 100 or 1,000 times harder than that in terms of the size, the brightness, also the amount that it will have appeared to move on the sky. So distinguishing it from a faint star will be really challenging. And so we need to know where to look. And before, when we had basically 2 data points, maybe a couple of others, we didn't have a good idea. Now we still don't have a good idea, but we're like 1 data point closer. And if we can do the same thing 50 more times, then that will really help sort of narrow down the part of space that Planet 9 might be in if it actually exists.
Right. And I know that the team that actually were behind this wasn't Badigan and Brown, but it's Chad Trujillo and David Tholen, and both of those are quite experienced planet hunters. I've seen their names come up quite a bit in a lot of these press releases. So,
and just to kind of, I'll tack on one thing, just kind of give a sense of how hard a problem this is. They found this object 80 AU away using the Japanese Subaru telescope, which is an 8.4 meter telescope on Mauna Kea. Basically doing the same kind of asteroid searches that we use really small telescopes like Pan-STARRS, which is like a meter across, to do for objects in the inner solar system. Just to find something 80 AU away, 300 kilometers in size, we basically needed one of the largest telescopes on Earth today. To find Planet 9, we're talking about finding something bigger, but that's 1,000 AU away. We really, really need larger instruments, even if we know exactly where it is, to find that little point of light.
Yeah, there's 2 parts to this, right? There's whatever is the gadget that's going to actually find it, and that could very well be something like the Large Synoptic Survey Telescope, probably has the capability to find it, and then you're going to be turning all of the biggest telescopes in the world on it to try and understand it any better once it's been found. But this really is the limits, and this is the way this works. As the new instruments come online, that's when you get the big flurry of new discoveries. We're still waiting for the new instruments to come online, and they're all going to come online in the next decade. So
it's an exciting time.
Buckle up. All right, Kimberly, exomoon?
Exomoon. Maybe exomoon. So here's the story. Back last year, you may have heard of a potential exomoon called Kepler 1625b-I. To figure out a better way to say that. But there's a team who's been hunting for exomoons in the Kepler data. The theory being that if there is a planet that transits, and if that planet has a moon around it, the moon might also transit the star, and Kepler may have seen it. This team after searching through hundreds of Kepler light curves for planets that might host a moon that we might be able to see, they found one compelling target, Kepler 1625b. And they applied for Hubble time last year. And then the media sort of grabbed it and said, oh my God, an exomoon. And they went, no exomoon, not yet. Let us look first. And just today, actually, earlier today, they released the results of those Hubble observations that got everyone so excited last year. And lo and behold, the Hubble observations of the transit of this Jupiter-sized planet support the idea that there may be a very large exomoon around that exoplanet, which is super exciting. I did a little bit of happy dance when I saw it. I was like, yay. It's not, well, the story is it's not ruled out. It's not a slam dunk exomoon. Everything that all the data that they have and all of the theories that they've tested all support the idea that there is an exomoon. And according to them, the exomoon hypothesis performs so much better than any other idea that they've been able to test, whether it's because of stellar variations, whether it's a spacecraft effect, whether there's another planet in the system that may be causing some similar type of signal. None of those theories do as well as the idea that there is a large Neptune-sized moon around this Jupiter-sized planet.
So it's interesting.
Let me
It's sort of
ask-
like that same time when they first discovered the hot Jupiters, at the very beginning of their ability to make these techniques, they were able to find really the most massive planets
The most
orbiting.
massive planet in the most likely orbit that they could detect with that technology.
Yeah,
exactly.
orbiting
It's very
really, really
analogous
close to
And-
that, to the
and-
star. And so to
and
now
it-
have
it's
a Neptune-sized moon orbiting
It's
a
a very
Jupiter-sized
big
star.
moon around a planet that's
Yeah.
the size of Jupiter.
Yeah.
In terms of size ratio and mass ratio, it's sort of similar to our moon to Earth in terms of size and mass ratios, but scaled up by a factor of about 11. It's huge. We have no moons in our solar system that are as big around Earth. I mean, Jupiter's moons are tiny compared to Jupiter itself. And none of our moon formation theories that we see in our, we have examples of in our solar system really fit this sort of scenario. So yeah, it's very analogous to when we first saw hot Jupiters and we said, what the heck is a planet doing there? We never expected a planet to be over there. And we're like, this is a weird moon. Never expected a moon to look like that over there.
Can you talk a bit about technique to find it?
Yeah. So they first detected it using the Kepler data. So they saw the transit of this Jupiter-sized planet. It's around a sun-like star, very old, about on a 1-year orbit. And they noticed in some of the Kepler data, there was an extra little dip in the light offset from the planet itself. And they said, that sort of looks like what a moon would look like. Let's go look more. And so they looked with Hubble at a 4th transit of this planet. They looked in many wavelengths and they got about 40 hours of Hubble time, so very expensive in terms of observational time. And they observed the transit of the planet, looking to see if there were any anomalies that might point to an exomoon. And they found 2 really compelling lines of evidence in the Hubble data that supported the moon. The first is that they did see that extra transit dip exactly where they expected to see it. So that was good. And the other piece of evidence is that there was actually a transit timing variation that they were able to measure. What that means is that what they propose is that this massive moon was actually tugging gravitationally on the planet and shifting the time when it actually transited the star. And they measured an hour and a quarter difference from when they expected the transit to happen to when it actually happened. And that's how they get the idea of how massive the moon might actually be. And when they put all those together and try and fit all of those data into one theory, exomoon is the theory they get.
Is Hubble very good at this kind of thing? It's not really that great as a transit detecting
It's not very
telescope.
good as a transit survey, but in terms of taking transits of planets you know are there and you have a good idea of when they're going to happen, Hubble is very good at it, actually. It's for this particular star, it was about 4 times as precise in terms of getting a brightness variation than Kepler did. And for some other stars, it can do even better. And that's because Hubble is, in and of itself, it's a much more precise instrument than Kepler ever was.
Let me ask in an innocent question.
Oh God.
So, all the way back in 2006, we demoted Pluto from planet because it had a moon about a tenth the size of it, and we said that's more like a binary planet than it is a planet and a moon. I just mashed words into my keyboard, and Neptune is about a third the size of Jupiter by radius.
Yes.
So does that mean we have to call this Jupiter-sized planet a dwarf planet?
So I will say, when I actually attended this press conference and someone actually asked this question: is this a binary planet or is this really a moon? The answer they gave was, does it really matter what we call it? As far as their calculations, the moon itself, the barycenter of the moon and the planet is within the planet, which it's not for Pluto. Pluto and Charon, the barycenter is outside of Pluto's physical radius, and so it's binary. For this one, the moon's barycenter is within the physical extent of the planet. The moon orbits very close to the planet. We're calling it a moon. It's a satellite of some sort of this planet, and I'm sure we'll come up with some more compelling or more precise terminology once we actually know that this thing really exists.
Well, would you anticipate that it's cleared its orbit? That's really what you would
and
be
how will
for.
we ever know for an exoplanet system?
Yeah,
which is one of my big
beefs
about the whole planet definition thing. But that's a whole nother kettle. I'm not going there.
Well, that's awesome. I know David Kipping was behind this work.
So this is David Kipping's work. David Kipping and his graduate student Alex Tichy, who've been working on this for a very long time. They've proposed for more Hubble time for next year. The planet is scheduled to transit again in May of next year, and they're hoping to get Hubble time. They're hoping to get even get more observations, not just with Hubble, but maybe with other space telescopes or ground-based telescopes, get as many lenses pointed at this thing as possible, try and actually pinpoint if this thing is there and if it matches the predictions of what the transit should look like.
Why are exomoons so important?
Exomoons are so important because they're a fundamental part of our own solar system. We want to know, one of the big questions is, are we normal? Is our solar system normal? And what we see here is satellites everywhere. Every single planet, and some dwarf planets and some asteroids, except two lonely planets, have a satellite of some sort. It's ubiquitous in our solar system, and we want to find them elsewhere to understand why they're there, and how common they are. And I mean, in terms of habitability, if you have a rocky planet, a rocky moon around a gas giant planet in the habitable zone, that moon might be habitable too. Who knows? But it's one of those fundamental things, like, is what we see here common elsewhere, giving us an idea of why things are the way they are.
Yeah, and you've got this idea that there are let's see, I'm not sure what's happening on there. You've got this idea that there are that various planets with their moons, that might be a necessity for you to be able to have life. So if you potentially are going to have a planet like Earth, an Earth-like world in the habitable zone, maybe you need to find that moon, that exomoon, to help with the idea of that there's going to be life there. So that's another.
I mean, even with Jupiter and its icy moons, we know that there's subsurface water there that may host life too. I mean, habitable is not just, a tiny ring of the right temperature around a star. Habitable could be so much more.
Yeah.
I was about to log off, but since you brought up the astrobiology and the moon, do you want to hear anything about?
Sure, yeah. Feel free to jump in.
That's actually in the book about did the moon help not only the origin of life, but the also keeping the planet stable enough for very sophisticated life, including intelligent life, to emerge. So, if you think of an exoplanet in the same sort of situation, if there's a stability issue, that's a factor. There's also a factor related to ocean tides, because you might have that mixing that went on. If you're talking about an in situ origin of life, on that planet. If you're talking about seeding through a transpermia event, maybe then it doesn't matter. But the ocean mixing may very well have something to do with the origin of life. And because our moon was maybe way closer, they think it could have been as close as 25,000 kilometers around the time of the origin of life. The amount of the distance that the tides traveled back and forth on the land would be measured in kilometers instead of just a few meters. Now might have helped. And there's the stability is, let's say you spin a top or a fidget spinner, a dreidel, anything like that. Well, it starts to wobble and it goes slowly. And the effect of the moon kind of is like that on the Earth. And if we were wobbling a lot more because we didn't have a moon, we'd have way, way, way greater shifts in climate. Could multicellular life, and especially life with brains, really survive that? That's a big question.
Yeah. Paul, someone won a Nobel Prize. Was it you?
No, once again,
Gosh.
the Nobel Prize Committee is led astray. Fools, all of them.
I'm
They
I'm
did
sorry,
a
Paul.
pretty good
I
job
sent them a
this time
letter.
around.
I sent them a letter on your behalf,
I know
but I'm
you guys
sorry.
sent letters of support.
Yeah.
It turns out they don't care about you either. Sorry to break it to you this way, but no, it was awarded to three very, very deserving people. We've got Arthur Ashkin of the US, Girard Moreau of France, and Donna Strickland of Canada for not just playing with light and understanding light, but really developing techniques with light that have enabled so much fantastic technology and capabilities that we take for granted now. Most of this was developed back in the 80s. So Arthur Ashkin, on one side, he gets half the prize because he accidentally invented something called optical tweezers.
Yeah.
Where you think if you blast a laser at something, it will either heat up or explode or at the very least get pushed away. But if you tightly focus a beam of light, there's a narrowest part in that beam of light, and we call that the waist. And particles can actually get trapped in that waist and get held in suspension. And so you can point this tightly focused beam of light at an atom, a molecule, or even a virus, and pick it up and move it around exactly as if you had a tiny little pair of tweezers, which has enormous applications in modern biology.
Like a tractor beam.
It is a literal tractor beam if you are tiny.
That's so awesome.
Yes, that's half the prize. The other half of the prize was shared between Girard Burrow and Donna Strickland. Donna was a graduate student of Girard back in the 80s. By the way, this was her very first scientific paper ever as a graduate student, which eventually led to her winning the prize. Go grad students, way to hang in there, Donna, playing the long game. What they developed is something called chirped pulse amplification, where if you have a pulse of light and you want to make it a really, really powerful pulse of light, you usually end up blowing up your light emitting apparatus. Can't handle that energies. There's all sorts of cool nonlinear effects. So she and Girard developed a technique where you take this pulse of light, you stretch it out first, then you can amplify that very, very safely, and then you squeeze it back together. And this has led to the development of things like femtosecond pulse lasers, where the most powerful lasers in the world, but delivered on very, very short time scales. And this has unlocked advanced communication, advanced materials, drilling and manipulation, and even LASIK eye surgery, all trace their routes to this research.
Wow. All right.
And
wow, I
gotta say, because Donna Strickland, Dr. Strickland, is only the third woman in all of history to win the Nobel Prize in physics, the first woman in 55 years to get the prize.
Kudos to her.
Yeah. Yeah, I like she calls herself a laser jock.
Laser jock.
Yeah. Well, congratulations to all of the Nobel Prize winners. Next year, Paul, that'll be your year.
I'm hoping because I wrote that one paper as a grad student that
First
was
name
pretty
on it.
good.
Yeah.
Was pretty good.
Yeah.
My first paper as a grad student, I don't think will ever be Nobel Prize worthy. No.
Honestly, mine either. Me
Sure will. You all stand a chance. All three of you stand a chance of.
We should write a paper together that will triple our chances.
Yeah.
No.
Let's talk briefly about Hayabusa and we've been all just kind of really enjoying the latest series of images and videos that are coming back. And I'm just going to show people a couple of them. And the first one I want to show you. So for people who just bring people up to speed, of course, the Hayabusa 2 is the second Japanese mission to an asteroid. The first one had all kinds of problems, was able to limp back to Earth with just milligrams of asteroid sample. The new one is going back, learning from all the lessons they learned on the first mission. They're sending 4 separate landers to the surface of asteroid Ryugu, and 2 are already down on the surface now. 2 more to go.
3, I think 3 are down there right now.
3 down, 2 Japanese, 1 German, French, and then 1 more to go. And they are, Paul and I, when we were doing the Astro Tour, we had a conversation about this on the ship, and the way that the Japanese are running this mission couldn't be more different than a NASA mission. They are willing to just run these wacky experiments just to, let's just try a whole bunch of different ideas to see what works.
It's awesome.
And it's working
so much fun.
Great. So I just want to show you a video of from the surface of the asteroid, and it's a mind-bending look here. And so some people have actually stitched this together into a video, and apologies to the... Well, let me see if I can pull this off here. Let me see. There, this is for you guys. So you can see, the joke, of course, is that sending J.J. Abrams to the surface of the asteroid was a bold move, but I think it worked out. We'll run this again. Just look at that lens flare.
It's a professional-looking lens flare right there.
Yeah, it really is. So that's one, and these are from the twin rovers that the Japanese spacecraft had sent down. The other one here is, I've got this up here as well. And this is the Mascot Lander, and this is the one that is which has just landed last night. I don't know if people can see this. So we don't have any images that I've seen from the surface of it yet, but this is like the last image that it took just as it was coming into the surface, and it just looks, I don't know, like crusty bread, or like, I don't know what it's got, just this sort of really
looks like the
surface.
rind of Parmesan cheese.
Rind of Parmesan
like
cheese.
Nice big wheel.
Yeah.
Wait, Paul, do you like cheese?
Yeah.
Oh,
cheese.
We talk about cheese.
But
So
seriously, pictures from the surface of an asteroid.
yeah.
How flippin' cool is that?
Yeah,
Love
absolutely. So what's really interesting about the Mascot Lander, which I really enjoy, is the lander lands on the surface of the asteroid, and then it hops randomly to a new location, and then there samples the temperature, looks around at its surroundings, and then when it's ready, hops again, and just wherever it ends up, it's going to be interesting. So why bother trying to pick a target?
Hey, Fraser,
It's like fillet, but on purpose.
Yeah.
Hey, Fraser, if it's a random walk, does that mean it will only explore 30%?
Only
of
30% of the entire asteroid
But if you have 4 rovers doing random walks in different directions, is that still
That's
only 30%?
120%.
Yeah.
It's 120%.
I think that is. I forget if you
That's just
add up
science.
30% 4 times.
But I
Someone do
think
the math.
the 2 Japanese rovers, they're like little, tiny little, like frisbee-sized rovers. They're really actually very tiny, and they also do the hopping thing. And what you can see, it's kind of an ingenious move. You blast off a little bit from the surface, the low gravity and the asteroid's rotation takes you about 15 meters. You set down, 15 meters away from where you were before, and you get to take all these great new measurements. but you also don't run into things like boulders and, craters and stuff, hopefully.
Yeah,
But it makes it a lot easier to move around a
this
surface if
mission,
you don't
right?
know what it is ahead of time.
You've got an ion engine powered spacecraft that has gone into orbit around an asteroid, has deployed 4 or will eventually deploy 4 landers to analyze the surface, and it's going to be doing a sample return. Like, that's the whole package. Like,
It's all of it.
Osiris Rex doesn't look so hot now.
And then maybe when it wraps up, it's going to do an asteroid redirect mission or something, right? just to sort of
nudge
wrap
it out of
everything
the way
up.
a little.
What's the cost to this mission?
Oh, that's a great question. I'm going to guess not much, but let me see.
75, $80.
Not as much as a NASA mission.
Yeah, that's where I'm going. Good call.
16 billion yen.
16 billion yen,
Yeah.
which is $1.6 billion. Or no, it's 100 yen.
$139 million. $140 million.
Wow.
Yeah.
That's like nothing.
I know.
Makes me sad. In the US.
Yeah. I mean, I think with the previous mission, right? With Hayabusa 1, it was, again, a fairly inexpensive mission fraught with failure. And in the end, they were able to pull it off. But a lot of people were giving them a pretty hard time. But this time around, they learned from all of those lessons. So,
and because it's so cheap, they could just
try
quickly iterate.
Yeah, just send a bunch more. So I'm anyway. I know that a lot of the really interesting stuff happened over the summer while we were offline. But now we're going to be on Hayabusa watch for the next couple of months as it continues to do its mission and as some of the new discoveries are made. It's a really impressive mission. Congratulations to everybody on the Japanese team that worked on it, and I can't wait to see what happens next. Ben Kalo is asking, does anyone know what the gravity is on the asteroid? It is very low. I know that you could throw a rock off of it. It's a very small asteroid. 10 kilometers? Teeny tiny. So... all right. Well, let's wrap up this week's episode of the Weekly Space Hangout. Before we go, of course, I want to give everyone a chance to shamelessly self-promote things that they're working on. Paul, you're on my screen right now. You've got a laundry list, I'm sure.
We'll focus on 2 things for now, 3 things for now, maybe 4. We'll see how we go. First off, my book is coming out November 20th. It is available for pre-order. Go to pmsutter.com/book for all the links and juicy info. And you can always go to my patreon.com/pmsutter to help support all my outreach and education activities. And the next Astro Tour we are looking at is the Costa Rica adventure with Mr. Fraser Cain. There's going to be telescopes. There's going to be volcanoes. There's going to be zip lining. There's going to be exotic beaches on the Guanacaste coast, and there'll be stargazing. It's fun for couples and families alike.
Yeah, right.
Go to astrotours.co for more info.
And we've still got some room, so... And then we can figure out when we will interview you for your book. I know you have to work out the logistics of this, so you'll come back and tell us more about what you're working on. Kimberly.
Yep.
Right. So I've been working hard most of this week about writing about this exomoon, which I was just so freaking excited about when I first saw it. And you can read all about that on eos.org. And upcoming, I'm also going to be working, talking about all of the wonderful different asteroid missions that are currently going on or are soon to launch. And you can also find that on EOS. And of course, follow me on Twitter at AstroKimCartier.
Morgan.
My fun project for the summer was serving as an editor for Crash Course Engineering, which, as someone who's been edited a lot in their life, was fun to turn the tables on someone and wield the hammer of power for a little while. But it's been a lot of fun. Engineering is cool, and it turns out it's also useful. So I highly encourage you to check that out. My episodes start, I think, with number 19, which just aired last week. And you can find that at youtube.com/crash course.
Awesome. All right. Now, obviously, since we're log rolling books, I just got the advanced copy. I got like a box of them. So this is the advanced copy of the Universe Today's Ultimate Guide to the Cosmos, written by Dave Dickinson, who's, of course, our astronomy writer on Universe Today. I did a lot of the work as well, edited his work, but also provided some content. But the thing that I did on this book, because, this is the part that I'm familiar with, painfully, was all of the photographs here are part of the astronomy, the astrophotography community on our Instagram page. And so what we did was I reached out to about 100 astrophotographers and had them contribute pictures. A bunch of names people are going to remember. So when you look inside the book, you will have never seen the vast majority of the pictures that are in this book. They were taken by amateur astrophotographers, and we were able to get them to license their images to us. And I think that's the part that I'm most proud of, is that all of the photographs in this were done by regular astrophotographers with skill and technique. So, because not everybody has the Hubble Space Telescope, so there actually aren't a lot of pictures that you've ever seen before in the book, which was a lot of work, but I'm really proud of it. So anyway, as soon as Dave and I get organized, we will be your special guests on the Weekly Space Hangout, and we'll talk about the book. So, but again, thank you everyone for joining us this week. A big shout out and thanks to everyone at the WSH crew, of course. They're organizing the chat, they're organizing the guests, and they are really keeping each other sane over the summer while we were on our hiatus. We couldn't do the show without you. And we really look forward to another wonderful year with all of your help. Nobody can see you, Paul. Nobody can see you right now.
Dang it.
We really look forward to another great year with all of your help. So if you want to be part of this community, really, they are the executive producers of the Weekly Space Hangout. Go to wshcrew.space. They will, you can find out instructions to join them, and they will be glad to help you join that community and be a part of it. So if you want to really help make this show, that is the way to go. All right, I'm going to wrap this up. I'm going to put us into the gallery view. There we all are. Now you can put your book up.
Now I can do it.
Yeah, there you go. There you go. Bye-bye, everybody. We'll see you all next week.